Hi, I am Truls Nordby at the University of Oslo, and today we will have a tutorial on ground shields and guards in measurements of electrical and electrochemical properties of materials with a lot of reference to the ProboStat sample holder provided by the Norex company. To do proper electrical measurements is to measure a voltage over your sample without additional external voltages and without losses on the way to your computer. And it is to measure the current through your sample without parallel currents. And if you measure impedance, it is to get the ratio between voltage and current without any of the sources of error in voltage or current. Such errors we term parasitics, and the errors to impedance and voltage are the series parasitics, and the errors to admittance and current are parallel parasitics. To reduce parasitic series impedances, we use 4 wires and up to 4 electrodes to do the measurements. To reduce parasitic parallel admittances, we use shields and/or guards. This webinar is a bit on wires and electrodes, but most importantly on shields and guards. When we talk about wires and electrodes to do the measurements, first we concentrate on measurements of impedance from measurements of voltage and current. The complex impedance is the ratio between the complex voltage and the complex current. If you do DC measurements, these are simple numbers, and if you do AC measurements, these are complex numbers. Measuring current and voltage in separate wires and with separate electrodes reduces parasitic series impedances. Now we will explain that. If we start with only 2 terminals, 2 wires and 2 electrodes, in a schematic it looks like this. You have the measuring instrument here within this box. It has a generator of current of some kind. This is fed through a circuit to the electrodes of your sample, 2 electrodes, and back. And the red color signifies wires where current is running. Current is going through a reference resistor, and the instrument measures the voltage over your sample via the wires going to the sample. And it typically also measures the voltage over the reference resistor. The measured voltage here is now a sum of voltages. It is the voltage over the contacts here and here. It is the voltage over the electrodes, over the wires. And then it is the voltage over the electrodes, and finally the voltage through the material. So this voltage is the current multiplied with the individual impedances of each source. The contacts, the wires, the electrodes, and the material. The current is the same going through all of them. There is the same current, but it has different voltages depending on the impedance in each term here. So the total impedance you get from this ratio of the measured voltage and the current is the sum of the 4 impedances of the contacts, the wires, the electrodes, and the material. And seen from the instrument, this is the measured voltage divided by the current, and the current is the voltage measured over the reference resistor divided by the value of the reference resistor. It should be a small value, but it should be accurate and known to the instrument. So this is a normal 2-terminal, 2-wire, 2-electrode measurement. The next step of refinement is to go to an instrument which has 4 terminals, which is quite common when it is benchtop or more expensive instruments. Then the voltage is measured over two separate terminals. We can call them the high voltage and the low voltage terminals, while the current is measured through the high current and the low current terminals. The current is the same, again, through the whole circuit. We just call them high and low, starting from the high voltage side to the low voltage side. Now, since there is no current going through the voltmeter, because the voltmeter has a very high impedance, we draw them in blue, and there is now therefore there is no voltage drop here and here or here to the measured voltage. So now the measured voltage consists only of the voltage over the wires and over the electrodes and over the material. So now the measured impedance contains only the wires and the electrodes and the sample. So we have got rid of the contact, the terminal contact problem. We can go one step further. We can have 4 wires all the way up to the sample. Then we also get rid of the voltage loss in the wires, because now we measure the voltage here and there is no voltage loss in these wires because there's no current running here. So now with a 4-wire 2-electrode measurement, what we get is only the impedance of the electrodes and the material. Now we can split one of the electrodes into 2 electrodes, a reference electrode and a counter electrode. The reference is contacted by the voltage probe, while the counter electrode is supplying the current. Now the current is running through the sample like this, and we pick up the voltage between the working electrode and the reference electrode. There is no voltage drop in this electrode because there is no current running here. So this reference electrode picks up the voltage somewhere in here where there are current lines running between these 2 electrodes. So the measured voltage is now the voltage of the working electrode, this one here, and part of the electrolyte, part of the sample. And the impedance we measure is the impedance of the working electrode and part of the electrolyte. So this is the principle of the 3-electrode setup, commonly used in electrochemistry with ion conducting electrolytes, where we want to study one electrode and not both of them. You may note that there are different opinions on the validity of 3-electrode measurements and use of reference electrodes in solid-state electrochemistry, depending on this geometry. So this geometry that I show you here, the cross-section, is not fully accepted by everyone, and the exact measurement may vary depending on many parameters here. But the 4-terminal, 4-wire, 4-electrodes sample is well recognized. It is typically employing a bar sample like this. Here the current is running through the entire sample, but the voltage is now picked up inside the material. There's no voltage drop here because there's no current running here. So now we do not measure the voltage in the wires, not in the contact electrodes here. We only get the impedance in the sample material between these 2 voltage probes. So this is a way to get a true sample material impedance. The validity of this is straightforward for DC measurements, for single charge carrier, so that there's only one charge carrier that can go through the material, and where the contact resistances here are not many orders of magnitude higher than the resistance or the impedance of the material. Generally speaking, this kind of measurement can eliminate the contact resistance here, but there's a limit to how much resistance there can be here before the current that runs becomes so small that it is hard to measure something in here. If you use AC measurements, the 4-electrode measurement becomes ambiguous because of the different time constants of the electrodes and the material. And if you have mixed conductors here, it is not obvious that the current running reflects the true transport number of the different carriers and the true sum of conductivities, because the electrodes here may have a different transport number than the bulk material. There is another type of 4-electrode measurement called a van der Pol geometry. You can have a disk sample of some kind, and you can contact it with 2 current probes and 2 voltage probes. There's now current running here, and there are current lines going all the way through the disk. It's picked up by the voltage probes here. And under certain conditions of these being close to the edge, there is something called a van der Pol equation that can calculate the resistivity of the material based on the ratio between the current and the voltage. And this equation holds also for asymmetrical contacts and asymmetrical disk shapes. Then you just have to do 2 measurements where you rotate the current so that you do the current through these 2, for instance, and measure the voltage through these 2. Then the van der Pol equation does from these 2 measurements the correction of the geometry and gives you the proper disk material resistivity. This is something you can read about in papers from van der Pol and others. But I just notice again that the validity of this is only straightforward for DC measurements, for reasonably good contacts, for single charge carriers, and so basically the same as for the bar sample. But now we have talked about the way from 2 electrodes to 4 electrodes. Now let's move on to the shields, and we'll take one of the setups as example and add shields to the wires and look at how they work. So we will use the 4-wire 2-electrode setup, which is very commonly used by many to measure conductivities, for instance, of solid electrolytes and other materials. The shields are typically going around each wire when we have 4 wires. So we can draw it schematically like this. A dashed line here means a shield around the wire. So this thing here goes around the wire and shields it. This is often typically what we call 50 ohm BNC cables. And they are connected often in one end or both ends, so that, for instance, you can connect, in this case, the shields are going to the chassis of the instrument, and the chassis of the instrument is going to ground. So now we have grounded all the shields by their contact to the chassis. Shielded BNC cables typically look like this. This is the contact, and they may be connected to chassis to the ground in both ends. So here you see the BNC connector in both ends, or only in one end. Here you see, for instance, a typical set of wires for a potentiostat, where there's no shield connection here, only the center lead, which you can clip onto electrodes, for instance. So the typical thing with shield connection in both ends is typical for AC instruments, while single end contacts is typical for potentiostats, and we'll come back to later why that is so. So here's a long sentence. The shields, these, are primarily there to shield the measurement wires from each other, from the fields and induction from the applied voltage and current. They're there to shield from external electrical fields, from electronics, power supplies, transformers, power cords, furnaces, and from electromagnetic radiation like TV, radio, mobile phones, and many things. So it is partly to shield from each other, so that the current running here is not inducing signals in the voltage probe, but also from external signals and fields. Therefore, we try also to shield the sample itself and the sample holder itself. So here we show how the shields can also be connected to the chassis of a sample holder. So we also protect the sample against external fields when possible. In the ProboStat, that is not always possible because it goes to very high temperatures and must have ceramic tubes instead of metallic. We'll come back to that also. How can you know whether shields and chassis are connected? How can you know whether the shielded wire actually is connected to the ground of your measuring instrument? And how can you know that this shield is connected to the chassis of your sample holder, like the ProboStat? And I'm just saying first that you should use an ohm meter. You can measure it with an ohm meter. You can measure here the shield of the wire connector to the chassis and see if they're connected or not. And the same goes for the terminals at an impedance spectrometer, for instance. Here is the Solatron 1260. You can measure whether the shield is connected to the chassis somewhere. But you can also quite easily visually inspect it. You can look for an insulator ring, black or white, showing that the shield is insulated from chassis. If you look at the Solatron, for instance, you see there is a black insulator ring here and everywhere, so that these shields are physically separated from the chassis. But as you can see from this signal here, one shield, the shield around the generator output, is hardwire to chassis ground. On the ProboStat, you can recognize the shielded insulated shields by the white polymer rings here, or on the high temperature version, you can see them here. Then you know that this shield is not connected directly to the chassis here or here. If you want to have it connected, you must do it by a switch or by other means. If we look now at typical measuring instruments, the Solatron 1260 or the good old Hewlett-Packard 4192, and how they are connected to, for instance, a ProboStat. The ProboStat hot zone part is not shielded, first of all, so that you can see here that the sample is in a way unshielded, while the hexagon box of the ProboStat is shielded. So that the sample through the ceramic tube is quite vulnerable to furnace AC at 50 Hertz or 60 Hertz in the US. The base unit is often grounded via a stand or gas lines or other metallic objects. Shields are generally not connected to the chassis. I illustrate that here by showing that from the impedance spectrometer, it is connected to ground, but it is just going straight in and not being connected to the chassis here. So you need to think how to get them connected and how they will then help this one to get shielded. The spectrometer high current shield is hardwired to ground, so that is already connected to ground. The ProboStat, at least the newest version sold during the last 10-15 years, have switches that helps you to get control of this. The first one we mentioned is the chassis to high current shield switch. It is drawn here. When it is down, when you take the switch and put it down, it connects the ProboStat base unit chassis to the high current shield. So this switch down connects the chassis of the ProboStat through the shield of the high current wire to the chassis shield of the impedance spectrometer. So this is a way to get the chassis of the ProboStat connected to the high current shield. The default position of this is down. You should generally have the chassis of the ProboStat connected to this. We have another switch, the high current shield to low current. So there is another switch which connects the low current wire terminal of the ProboStat to the high current shield, which is always grounded. This you use to make the low current wire grounded and therefore connected to shield and therefore grounded. So if you want to have grounded measurement where this one is put to the same potential as ground, you put this switch down. But the default situation is to have it up, to have it not connected, to have floating measurements, so that all the wires and the whole sample are at floating potential compared to ground. This is the normal way of measuring. The third and final switch is the Shields bridge switch. Here you see the Shields bridge switch. It has 1, 2, 3, 4 switches connected to one physical switch. When down, it connects all the shields together. So this is the default to have down when you use Solitron instruments 1260 or a Hewlett-Packard 4192 and some other impedance spectrometers. Have it down and connect the shields together. We will show later why this is important. When you are measuring using, for instance, Solitron 1287 or other potentiostat, they have driven shields. Then this switch should be up so that the shields are separated. This is very important. Note that any bundled potentiostat impedance spectrometer system, whether separate or integrated, has the sample connected to the potentiostat part. Therefore, if you have an integrated or bundled separate system, keep shields separated. The shields bridge switch should be up on the ProboStat. But as I said, the 1260 and 4192 need connected bridged shields, and I will now explain why. The special thing with this impedance spectrometer is that the current returns in the current wire shield. What it means is that here goes the current. I will put on some arrows showing that the current is going from the generator through the current wire, through the sample, back through the low current wire, and back to the impedance spectrometer. The current is measured. However, instead of going back to the generator, it now returns and it goes back through the shield of the current wire it came from. Then it must go back here. I'll put on arrows to show this. Must go back here, back through the shield of the high current wire. Must go back this way, and then we complete the circuit. So in this way, you can see that there is now the same current going in this way inside the wire as the same current in the other direction in the shield. So there is now no net induction, no net field from this shielded wire. Therefore, it has no effect, for instance, on the voltage wire. So this is a way to make the measurement better. So when shields are bridged, so when these are connected together, you can have this counter flow, which makes it work. Current flows and cancels in shielded high current and low current wires. If the shields are not connected, no current flows. The only current that flows is a parasitic little, a capacitive little current that gives you maybe a measurement, but it will be very noisy and very bad compared to when you do it properly and connect the shields together and get the current back. So this is an important part of the operation of these impedance spectrometers. while on the other hand, potentiostats have driven shields. So now we go to the situation that you, for instance, have connected your sample through a 1287 potentiostat connected to an impedance spectrometer like this via the 3 wires that you use for this way of operating it. Now you have a completely different situation. Now you have shields coming out from the potentiostat, which are driven. You see that each shield here has a little amplifier connected to it that drives it with a certain potential. And we will see soon what potential. So now you must have the switch up. You must not connect these shields together, because then you are short-circuiting the outputs of these 4 different amplifiers. We will see later why they have these amplifiers, but for now, the important thing is just if you have a potentiostat connected to your sample, shields bridge up, don't connect the shields. There are other ways to do that than to have these shields bridge up. You can also ensure that you have wires where the shield simply does not go into the ProboStat. You can, for instance, use wires like this that come with a potentiostat. They end up in banana plugs. Then you, on the ProboStat, you put an adapter that converts the BNC of the ProboStat to the banana, either 2 or 1, and then you connect these to the red in both cases directly in here to the sample. In this way, the shields are not connected together. You are safe. Before we move on with them, we can just add that you can have additional shields and guards. The first thing you can do is to put an outer metallic tube instead of or outside of your outer ceramic tube. If you put a steel tube outside of the ceramic tube, you are getting, in a way, a separate box around your sample. This helps against external fields, and you get much less noise, especially for high impedance samples. You can also replace the ceramic support tube in the ProboStat with a metallic support tube. The metallic support tube will, in a way, guard, shield the wires going on the inside of it that goes up to the sample, so that you shield these 2 wires from these 2 wires. In a better way, you reduce the parasitic admittances, the conductance, and the capacitance. You can also use a surface guard. You can connect a ring electrode in the ProboStat to a ring electrode on your sample, and thereby guard away the surface conduction. If you have this kind of thing, what you do is to connect this surface electrode, this ring here, using the high current shield to low current wire. You connect this now to the shield system, and you connect the low current electrode to the surface guard electrode. And then for the lower electrode to the sample, you use the inner low voltage and inner low current, which are still available from the inside. Now, any current that goes on the surface will be led to ground, and therefore it does not count in the measurement. So you only measure what goes through the sample. This is used to eliminate or characterize surface conduction on a dense material sample. Now we will move to the effect and role of shields and guards in voltage measurements. Especially because what you have seen now is that in impedance measurements, it works quite fine with these shields to reduce noise. Now we will see that in voltage measurements, it comes out a bit differently. This is especially relevant and important for samples with high internal resistance. For instance, to measure the EMF over a poorly conducting ionic or mixed conductor in a chemical gradient to measure the transport number. Or to measure the voltage of a high resistance electronic conductor in a temperature gradient to get the Seebeck coefficient. But to understand that, let's go first back to the impedance measurement. Here is the impedance spectrometer again, our Solartron 1260, for instance, and all the shields and everything. And we are measuring now a very high impedance sample. So the shields are here to prevent noise and are often connected together for various reasons. Like I told you, we connect the shields together here to do the proper measurements in the Solartron. But the impedance between the wire and its shield is not very high. In fact, the impedance between the shield here and the wire here that goes inside of it is of the order of magnitude of 1 mega ohm. So in a way, we are now short-circuiting the two blue wires, even if they are supposed to pick up the voltage over a sample with 1 gigaohm. The two blue wires are short-circuited through their own shields, which are connected together. How can we then measure the sample impedances of such magnitude as 1 gigaohm? And the answer, very shortly put, is that this short circuit that goes via the shields are connected to ground and therefore eliminated from the measurement. That is not a very complete explanation, but it is a short explanation. So the impedance spectrometer is able to measure correctly even if it has a short circuit via its shields. And therefore you may often forget that your measurement setup has these short circuits. Because if you now move on to measure the voltage, the situation is different. Here I have now shown a voltmeter or a multimeter with some terminals. The important terminals are now only the voltage terminals where we measure the voltage. And let's say that this internal resistance of this voltmeter is 1 tera ohm. So it is in principle very well suited to measure the voltage over this sample of 1 gigaohm without causing much error because there's very little current running here. But as we have said already, the shields can be a problem. If these shields for some reason now are connected together via the shields bridge or quite simply lying next to each other, touching each other, they easily short circuit these two wires via the shields. And if the shields are connected together, you get typically, let's say 1 plus 1 is 2 mega ohm, and that will efficiently short circuit the 1 gigaohm sample. And the EMF you measure will only be 2 promille of what it should have been. The voltmeter does not take care of this. Okay, you can solve that by disconnecting or removing the shields, so that, as I have done here, they are not in contact with each other unless they are contacted with a chassis here. So in principle, this could go well. But inside the ProboStat, we have already the problem that the metal base unit of the ProboStat is a kind of a short circuit between the insulators that go through there. So you have maybe some mega ohm there, and that is then a problem, not for the impedance measurement, but for this voltage measurement. So what can we do about it? Then we come to high impedance voltmeters and potentiostats, which are then called electrometers, can apply driven shield guards. And by applying this, they operate as if they had infinitely high impedance. And that's why they are called electrometers, because they behave like old days electrometers, which was purely capacitive. What high impedance voltmeter and potentiostat with driven shield guards do is they put the shield at the same potential as the wire it shields. So the trick is to take the potential from the wire, feed it into an amplifier, a high input impedance amplifier and send it out to the shield. Now we obtain, without drawing any current, we obtain the situation that the wire and the shield are at the same voltage. When they are at the same voltage, no current can run between them. Therefore, there is now no short circuit current anymore between them. So even if these are in contact with each other in a way, we can still maintain different potentials here on this one, so that no current runs here, and no current altogether runs through the shields. So the shields are no longer a threat, no longer short-circuiting the wires. So they still do the job of shielding, but they don't short-circuit. So as I say here, for this we use a high input impedance operational amplifier on each shield, at least on one of them. Because if no current runs here, the danger is in a way not so big on this one. Then no current will flow, even if the impedance is low through the shields, the short circuit is stopped. In order to make this also apply to the ProboStat base unit, you need also then to make the metal part of the base unit a part of the driven shield guard. You do this by connecting the chassis of the ProboStat to the driven shield of a wire to one of the electrodes. For instance, using the chassis plus high current shield switch. So if you now connect the chassis of the ProboStat to the shield of the high current terminal, measuring the voltage, then you ensure that this is also part of the guard. You can notice that now I have used this high current terminal to measure the voltage. I am not going to explain in more detail maybe in how you necessarily do this, but one way would be to use this voltage terminal. No, let me say that again. You use the voltage terminal of the voltmeter in a normal way because it has the driven shield. Then the chassis of the ProboStat is also now guarded. However, it is often connected to ground via metallic tube, gas tubes, and other things. So in order for this to work, you have to disconnect any connection to ground. This can be a bit tricky. So in order to do this, you may need to isolate the base unit, use plastic gas lines maybe, and so forth. The use of well-guarded ProboStat base unit is you can read in a paper by Stubb et al. On surface protonic conduction in YSET in Journal of Physical Chemistry C from 2017. So with that, we close with a few final advices. When you have done everything properly with a ProboStat and you have gotten rid of all the noise and everything, maybe by a metal tube, outer tube, and you have grounded everything, you have one possible error left, namely the thermocouple. The thermocouple comes into the ProboStat from your temperature controller or temperature readout unit. And this thermocouple may act as an antenna that picks up noise on the outside and feeds it into the sample area. To get rid of this, it is you can try to ground the negative platinum thermocouple wire. This is usually not a problem for the temperature controller or readout unit, but it effectively removes signals coming into the sample from the thermocouple. Then you should be aware that some good actions you may take to prevent parasitic impedances, like using 4 wires, may have a negative effect if you are fighting parasitic admittances like cross conductance between wires, and vice versa. So that when you optimize for one thing, it may get worse for the other. So you should use a certain set of actions for high impedance samples and another set of actions for high admittance, high conductance samples. If you get very poor and noisy measurements, it can typically reflect bad contacts. For instance, remember that the 4-wire measurement with a Solutron or Hewlett-Packard require 8 functional wires, because you need the 4 wires and the 4 shields together, and both of them have contacts in both ends, so you need 16 functional contacts, and one of them can easily go bad or corroded or a loose wire. So if you have, so check that there is conduction through all the wires and all the shields. Poor measurements may also reflect that some wire somewhere is in accidental contact with ground. You want to ground the right things, but you don't want the 4 measurement wires to be grounded accidentally. And remember that the ProboStat system doesn't solve all the ground shield guard issues for you, but it provides the versatility with the 4 terminals and the 4 shields that allows you to optimize your measurements at high temperatures in controlled atmospheres. And with that, I thank for the attention this time. If you have questions or comments or inquiries, you may write to any of these or comment on the YouTube video.